In 1971, Motor Trend named the Chevrolet Vega its Car of the Year. By 1973, it was burning through engines faster than it burned through fuel. The aluminum block that was supposed to revolutionize American small cars was eating itself alive from the inside out, and the man who pushed it into production was the same engineer who built one of the greatest engines in automotive history. So, the late 1960s. America has a problem. Volkswagen is selling Beetles by the hundreds of thousands. Toyota and Datsun are quietly gaining ground on the coasts, particularly in California, where buyers were discovering that Japanese cars started every morning, did not leak oil onto the driveway, and could go 50,000 miles without anything important falling off. Detroit, the industrial capital of the world, the place that built the Mustang, the Corvette, and the 450-horsepower big block 427, cannot figure out how to build a decent small car. General Motors, the largest corporation on the planet, with more than 700,000 employees worldwide, is watching its domestic market share get chipped away by imports that cost half as much, weigh 1,000 pounds less, and actually work when you turn the key. The Big Three had tried small cars before. Ford built the Falcon, Chrysler had the Valiant. GM offered the Corvair, which sold well initially but became a public relations disaster after Ralph Nader targeted its handling in 1965. None of these were truly small by European or Japanese standards. They were shrunken versions of big American cars, designed by people who fundamentally did not believe Americans would accept a genuinely compact automobile. They were wrong. By 1968, imports held over 15% of the American market, and the number was climbing fast. GM's boardroom response was straightforward. We need a real small car, we need it cheap, and we need it yesterday. The irony was thick enough to cut. GM had the money, the engineering talent, the manufacturing infrastructure, and the distribution network to build the best small car in the world. What they lacked was patience, and that would make all the difference. Enter Edward N. Cole. Ed Cole was not some corporate suit who stumbled into the car business. This was the man who, as chief engineer at Chevrolet in the 1950s, oversaw the design and development of the small block V8. That engine debuted in the 1955 Chevrolet. It is still in production today. 7 decades later, hundreds of millions built. It powered everything from family sedans to Le Mans-winning race cars, to fishing boats, to generators. It might be the single most successful internal combustion engine design in American history. Before that, Cole played a key role in developing the 1949 Cadillac overhead valve V8, the engine that essentially launched the modern era of American V8 performance. The man knew engines. He had earned the right to trust his instincts. Cole also championed the Corvair and its air-cooled aluminum flat six, which had its own well-documented issues. That is a story for another day. By 1967, Cole had risen to president of General Motors. He was still an engineer in his bones, the kind of executive who showed up to the drafting room on weekends, but now he carried the priorities of management. And management wanted one thing above all else: speed. Beat the imports to the showroom. Beat Ford, who was developing their own subcompact, the Pinto. Get it done now. Cole had been tinkering with a small car concept using GM's corporate engineering and design staff for years, working independently of any division. When GM finally committed to building an American-made subcompact, they had competing proposals from Chevrolet, from Pontiac, and from Cole's corporate team. They picked Cole's version. This was not going to be a divisional car. It was a corporate project conceived at the top, then handed to Chevrolet to manufacture and sell. In 1968, GM Chairman James Roach made the public announcement General Motors would produce a new small car in the United States within 2 years. 24 months. For a vehicle that shared essentially nothing with anything else GM built. New platform, new engine, new factory processes, New automated assembly technology, new shipping system, everything from scratch. Cole assembled a dedicated design team headed by James G. Musser, Jr., a veteran engineer who had worked on the Chevy 2, the Camaro, the 350 and 400 cubic inch V8s, and the turbo-hydromatic transmission. Musser later said it was the first GM program where one person was in charge and a single integrated team designed the entire vehicle. 50 engineers divided into groups covering body, powertrain, chassis, quality assurance, and something GM called pleasability, which was basically a team dedicated to checking whether the car was actually nice to sit in. They worked exclusively on the Vega. The codename was XP887. The target base price was around $2,000. Chevrolet ran teaser ads starting in May of 1970 with no name attached, just the words, "You'll see." The car took its name from the star Vega, the brightest in the constellation Lyra. That 24-month timeline was aggressive by any standard. Several people inside Chevrolet thought it was reckless. They were not entirely wrong. The centerpiece of the whole project was the engine. Cole insisted on an aluminum cylinder block, not aluminum heads on an iron block, which was the conventional weight-saving approach used by plenty of manufacturers. A full aluminum block with a single overhead camshaft, a first for Chevrolet. And here was the part that made it truly radical: no steel cylinder liners. GM and Reynolds Metals, the aluminum company best known for Reynolds Wrap, had jointly developed a new alloy designated A390. It contained about 17% silicon by weight, along with roughly 4.5% copper and smaller amounts of magnesium. The manufacturing concept was that when you chemically etched the cylinder bore surfaces with acid after die casting, the process would selectively dissolve a thin layer of softer aluminum from the surface, leaving the harder silicon particles standing slightly proud, like tiny mountain peaks rising from a valley floor. These millions of exposed silicon crystals would serve as a durable wear surface for the pistons to ride against, eliminating the need for traditional pressed-in or cast-in iron cylinder liners entirely. On paper, it was genuinely brilliant. It saved weight. It simplified manufacturing. It eliminated about $8 per engine in liner costs alone, which adds up fast when you are planning to build 400,000 cars per year. And the basic metallurgy was not speculative. Mercedes-Benz and Porsche were using similar silicon aluminum alloys in their own engines with outstanding results. Some of those German engines lasted well past 600,000 miles without a rebuild. The concept was proven. The science was real. GM even claimed 6 million miles of engine testing before production. They installed pre-test engines in a Fiat 124 sedan for initial development and ran several 1968 Opel sedans for drivetrain testing. 6 million miles sounds like a lot. It was not enough. The problem was everything else. Cole wanted this engine done his way. He visited the engineering staff drafting room on Saturdays, personally reviewing drawings and directing design changes, to the considerable frustration of the Chevrolet engineers who were supposed to be finalizing it for production. Chevrolet's own engineering group had developed an alternative engine that would have been cheaper to build, more conventional in its approach, and almost certainly more reliable in daily use. Cole overruled them. His corporate engine, his aluminum block, his way. The Chevrolet engineers knew he wanted speed above all other considerations. They also knew that contradicting the president of General Motors was not a path to career advancement. And here is where the cost-cutting began its slow, fatal work. To save money on a car already being squeezed on every conceivable margin, GM decided to pair the aluminum block with a cast-iron cylinder head. Two different metals, two very different coefficients of thermal expansion. When aluminum heats up, it expands roughly twice as fast as cast iron. So every time the engine reached operating temperature, the aluminum block was growing at a significantly different rate than the iron head bolted on top of it. This subjected the head gasket, the critical seal between the two components, to enormous cyclical stress. The Vega's head gasket was designed to be adequate under normal thermal conditions, but the Vega would rarely experience normal thermal conditions, because the cooling system was barely adequate. Cole initially believed and argued forcefully that the engine did not need a radiator at all. Yes, seriously, he thought the heat rejection from the heater core alone would be sufficient to maintain operating temperature. After multiple prototype failures proved this to be dangerously wrong, a radiator was grudgingly added to the design, but it was small, about 12 inches by 12 inches, the smallest radiator you could reasonably bolt to a 2.3-liter engine, and still call it a cooling system. There was almost zero thermal margin. If the thermostat stuck closed for 30 seconds too long, if a hose developed the smallest pinhole leak, if the coolant level dropped half a quart below the proper fill line, the engine temperature would spike past the point of no return. And when this engine overheated, the consequences were not just expensive, they were terminal. The aluminum block featured what engineers call an open-deck design, meaning the cylinder bores were essentially freestanding columns within the block, unsupported at their tops. In a closed-deck design, the tops of the bores connect to the outer block walls by solid bridges of metal, providing rigidity and resistance to distortion. The Vega lacked this. GM had actually designed a superior aluminum cross-flow cylinder head, called the L10, with hemispherical combustion chambers and better thermal characteristics. It was lighter, about 4 inches lower, and would have eliminated the iron-aluminum expansion mismatch entirely. Prototypes were built, manufacturing tooling was started, then it was killed. The cast iron head was cheaper. When the engine overheated, and it overheated often, the aluminum block expanded faster than the iron head. The head gasket breached. Coolant seeped into the combustion chambers. Now coolant is many things. A lubricant is not one of them. In a conventional iron block engine, a blown head gasket is expensive but survivable. Annoying. A weekend in the garage. Pull the head, replace the gasket, resurface the mating faces, reassemble. With the Vega, the coolant attacked and scored the unlined aluminum cylinder walls permanently. There were no iron sleeves to absorb the damage. Once the bore surfaces were compromised, the block was scrap, not rebuildable, not machinable to accept oversized pistons. Done. A $2,000 car with a disposable engine, and the engine had other problems stacked on top of that fundamental one. The valve stem seals were poorly designed and failed early, allowing engine oil to leak past the valve guides into the combustion chambers. Owners saw blue smoke from the tailpipe, that unmistakable signature of an engine burning its own oil. Some Vegas consumed a quart every few hundred miles, brand new. The overhead camshaft was driven by a timing belt rather than a more durable chain, and the belt was not covered under warranty. Owners were expected to replace it at their own expense. When it broke, which it did with some regularity, the results were not gentle. The base carburetor was a cost-driven single-barrel unit that starved the engine for fuel under load. Even the transmission was a compromise. GM's finance department insisted the base gearbox be a cheap 3-speed manual, with the more desirable 4-speed offered only as a profit-generating option. Opel, GM's German subsidiary, was commissioned to develop the 3-speed from scratch specifically for the Vega, an unusual expense for what was supposed to be a budget car. The engine vibrated so badly that Chevrolet added heavy dampers, acoustic coatings, and layers of sound insulation to mask the roughness, adding weight that nearly erased the savings from using an aluminum block in the first place. Internal nicknames for the engine included the world's tallest, smallest engine, owing to the unusually tall cylinder head, and the engine backfired through the exhaust with enough concussive force to to rupture the muffler. Chevrolet's first Vega recall, campaign number 72C05, addressed exactly that. 130,000 cars. By May of 1972, 6 out of every 7 Vegas produced had been subject to at least one recall. 6 out of 7. That is not a typo. The factory assembling all these cars was supposed to be a showcase of American manufacturing. Lordstown, Ohio. GM invested $75 million upgrading it into what was arguably the most automated auto plant in the world. Roughly 95% of each Vega body's 3,900 welds were performed by industrial robots called Unimates. The production target was 100 cars per hour, one Vega every 36 seconds. Nearly double the pace of any other GM assembly plant in the country. The car was designed from the start for this kind of speed. Modular body construction. 50% fewer body parts than a full-size Chevrolet. Computer-monitored quality control. On paper, it was the factory of the future. Then, in October of 1971, GM's newly formed assembly division, known internally as GMAD, took over management of the plant. The workers had a different name for the acronym Get Mean and Destroy. GMAD was born from a ruthless calculation. For every additional half-second of labor extracted per hour across the plant, GM saved $1 million per year. Their first move at Lordstown was to lay off approximately 300 workers and redistribute their tasks among the remaining staff, while pushing line speed even higher. The average age of a Lordstown worker was 24. The union president was 29. These were young, educated people with long hair and bell-bottoms, and they were not interested in being treated like interchangeable parts. Absenteeism spiked. Workers began letting cars pass their stations without completing their assigned tasks. Then came outright sabotage, upholstery slashed, windshields deliberately cracked, ignition keys jammed into locks and broken off. The repair lots overflowed with defective Vegas until there was physically nowhere left to park them. Managers were forced to stop the line. GM absorbed roughly $40 million in lost production before any formal labor action occurred. On March 4, 1972, 7,700 Lordstown workers walked off the job. The strike lasted 22 days. It cost GM an estimated $150 million in lost Vega sales. Newsweek called it an industrial Woodstock. The national press invented a term, Lordstown Syndrome, describing the growing revolt of American workers against dehumanizing assembly line labor. The Senate held hearings. Ted Kennedy introduced the Worker Alienation Research and Technical Assistance Act. Cars rolled off the line during this period with torn seats, scratched paint, missing bolts, and worse. The Vega was supposed to beat the Ford Pinto and the AMC Gremlin. Instead, it was losing ground to both, and to the Japanese imports it was specifically designed to stop. The car's reputation, already wounded by the engine, took another blow from which it would never recover. If you're enjoying this, hit subscribe. We cover stuff like this every week. Okay, back to it. Now, let us talk about what was actually happening inside that block at the molecular level, because the engineering story is fascinating, even when the outcome was a disaster. The A390 alloy contained roughly 17% silicon, 4.5% copper, and trace magnesium within an aluminum matrix. Silicon, at the crystalline level, forms extremely hard particles distributed throughout the softer surrounding aluminum. Think of concrete. The aluminum is the cement. The silicon crystals are the aggregate providing structural hardness. After die casting, the cylinder bores underwent chemical etching with an acid solution that selectively dissolved aluminum from the surface. What remained were millions of hard silicon particles standing slightly above the surrounding metal, creating a microscopically textured surface that retained oil and resisted wear. The pistons were aluminum, electroplated with a thin layer of iron. Iron-coated pistons sliding against silicon-studded bores. No liners, lower weight, lower cost. So what went wrong? The acid etching process demanded laboratory-grade precision, etch depth, acid concentration, temperature, exposure duration. Every variable had to be exactly right. Too shallow an etch meant insufficient silicon exposure and premature bore wear. Too deep, and the silicon particles detached from the aluminum matrix entirely, transforming from protective bearing surface into loose abrasive that actively ground away the piston coating. At production rates exceeding 100 engines per hour, maintaining that precision on every single block was essentially impossible. Quality varied wildly. Some engines were perfectly finished and would have lasted 100,000 miles. Others were compromised before they ever left the factory. The thermal mismatch between iron-plated pistons and aluminum bores compounded the problem. In cold weather, excessive clearance caused piston slap, the hollow knocking sound Vega owners learned to dread every winter morning. As the engine warmed and the aluminum expanded, clearances changed unpredictably. This constant thermal cycling stressed both the bore coating and the piston plating thousands of times per year. Eventually, the iron layer wore thin. Once bare aluminum piston met silicon aluminum bore without the protective intermediary, scuffing progressed to seizure in short order. The open-deck block design amplified every weakness. Unsupported cylinder bores distorted under thermal stress. Out-of-round bores leaked past the piston rings, increasing blowby and oil consumption while dropping compression. The engine consumed itself in slow motion. Base compression was 8-to-1, lowered from the original design target to meet emission standards for unleaded gasoline. Output was roughly 70 horsepower in single-barrel form, about 90 with the two-barrel carburetor. For 2.3 liters, those numbers were modest, even by 1971 standards. Mercedes and Porsche avoided this cascade of failures with three differences. All aluminum construction eliminated the thermal expansion mismatch between block and head. Tighter manufacturing tolerances ensured consistent bore quality, and robust cooling systems provided proper thermal margins. Same alloy family, same basic concept, completely different engineering discipline. The Vega did not fail because the science was wrong. It failed because schedule pressure, budget constraints, and corporate pride conspired to skip the steps that separated a working engine from a self-destructing one. The consequences spread outward for years. Touching every part of GM consumer trust collapsed within the first two model years. John DeLorean, Chevrolet's general manager at launch, later admitted he felt compelled to promote the Vega well beyond his personal confidence in it. He described a corporate environment where identifying a problem was punished more severely than causing one. DeLorean eventually left General Motors entirely, deeply disillusioned by what he had witnessed. His account, published in the 1979 book On a Clear Day You Can See General Motors, remains one of the most damning insider portraits of American corporate culture ever written. GM did not fix the engine's core defects until 1976, 5 years. The revised Dura-built engine featured an improved head, better cooling passages, and upgraded gasket sealing. GM backed the '76 Vega with an extraordinary 5-year, 60,000-mile warranty. They ran 3 pre-production hatchbacks non-stop through the California and Nevada deserts for 60,000 miles each, in ambient temperatures reaching 122 degrees Fahrenheit. The engines held up. The only failure was a broken timing belt. It was a genuine engineering redemption, and it was 5 years too late. Nobody was listening anymore. In 1972 alone, GM issued 3 mass recalls. The largest covered 500,000 cars. The bodies rusted aggressively due to defects in GM's new electrophoretic primer process, which left air pockets around body contours that blocked proper coating. The Vega became known as the car that started rusting on the showroom floor. In 1978, Congress held hearings specifically addressing the Vega's overheating. Despite everything, Chevrolet moved over 2 million Vegas across 7 model years. Sales peaked at 460,000 in 1974, driven by the oil embargo that made gas guzzlers temporarily unsaleable. People bought the Vega because they needed something, anything, that got decent mileage. Many of them regretted it. The Vega story also influenced how America thought about its own industrial competence. Here was the world's largest automaker, backed by billions of dollars and thousands of engineers, beaten at the small car game by Toyota and Datsun, companies that most Americans had never heard of a decade earlier. The Vega did not just damage GM's reputation. It shook the assumption that American engineering was automatically superior. That psychological shift mattered. It opened the door wider for imports and changed the competitive landscape of the American auto industry permanently. The car produced one beautiful exception, the Cosworth Vega. A partnership with British engine builder Cosworth Engineering yielded a dual overhead cam, 16-valve aluminum cylinder head with Bendix electronic fuel injection. The Cosworth head was all aluminum, eliminating the fatal thermal mismatch. Only 3,508 were built. They cost nearly twice the price of a base Vega and sat just $900 below a Corvette on the dealer's price sheet. Not exactly economy car territory. Each engine was hand-assembled in a clean room at the Tonawanda, New York plant, the same facility that had once built the legendary ZL1 all-aluminum 427 big block. 30 Cosworth engines per day. In racing trim, the Cosworth block made 260 horsepower and won 2-liter class races. It proved the concept worked when done properly. One more detail that captures the whole story. The Vega was engineered to be shipped standing on its nose. GM and Southern Pacific Railroad developed the Vert APAC rail car, which held 30 Vegas vertically, nose down, versus 18 in a standard auto rack. 40% reduction in shipping costs. Engineers designed an oil baffle for the number 1 cylinder, repositioned battery caps, added a carburetor drain tube, and angled the windshield washer bottle at 45 degrees. They designed an engine to function while pointing straight at the ground during transit. When the Vega was discontinued in 1977, the Vert APAC railcars were scrapped. They were too specialized to carry anything else. A purpose-built shipping system, retired because the product it was built for could not survive its own engine. Remarkable work. They solved the shipping problem completely. They just never quite solved the running problem. GM's next small 4-cylinder was the Iron Duke, cast iron block, no aluminum experiments, no sleeveless bores. The name itself was deliberate distance from the Vega engine, heavy, unrefined, about as exciting as a lawnmower. But it ran for 200,000 miles without complaint if you changed the oil. After the Vega, that was exactly what GM needed. Boring reliability. The Cadillac division apparently did not get this memo because in the early 1980s they produced the HT4100, another open-deck aluminum block with iron heads, and it suffered many of the same warping and gasket failures. Some lessons take more than one teaching. The irony is that aluminum block engines eventually became the global standard, exactly as Cole envisioned. Today, almost every production car engine uses an aluminum block with iron liners or plasma-sprayed coatings. Direct descendants of the concept Cole championed. The technology was right. The timeline was wrong. The cooling was inadequate. The decision to pair an aluminum block with an iron head to save a few dollars per unit on a $2,000 car was the choice that killed it. Ed Cole retired from GM in 1974. He died in 1977 in the crash of a small plane he was piloting. He was 71 years old. He never publicly acknowledged the Vega as a failure. The engineer who gave America the small block V8, one of the finest engines ever designed, also gave it the Vega 2300, one of the worst. Same mind, same confidence, Same willingness to bet on bold ideas. Different result. The small block succeeded because Cole had time, because Chevrolet's engineering team had room to test and refine, because nobody was breathing down their necks demanding a finished product in 24 months. The Vega failed because none of those things were true. Sometimes the distance between a legend and a cautionary tale is about $8 worth of cylinder liners and a radiator that was a few inches too small. And there you have it, the Chevy Vega, named after one of the brightest stars in the sky. The word Vega comes from Arabic, from a phrase meaning falling. You cannot make that up. If you enjoyed this one, subscribe. We do these deep dives every week. Got a Vega story of your own? Maybe your dad owned one. Maybe it actually lasted. Drop it in the comments. I would love to hear it.